our next speaker is Marco Badini, who's going to tell us about the Vietoris endofunctor for closed relations.
Thank you, Luca. Okay, so I have a question for you. Okay, what's special about this picture? Can you see it?
Yes.
Upside down. Okay, yes. If you turn it upside down,
you can see it one way and another.
it still makes perfect sense. Exactly. Other questions? Yeah, it has a nice little picture. Okay, what's so special about this picture? You can see I hate myself.
Try the same.
Try the same, exactly. Still we get a dual which makes perfect sense. That is great. It's even very optimistic. Okay, next question. What's great about the Vietoris? Okay, yeah. Same thing. If you turn it upside down, the dual still makes perfect sense. And that's the main message. So the Vietoris has a nice dual. So this is already known, and our contribution is just this addition, this footnote here, that this is true even for closed relations. Now I'll tell you also why we got interested into closed relations and where the tricky parts are. Okay, so what do I mean by dual in this case? Well, this is stone duality. Stone duality between stone spaces and Boolean algebras. Stone spaces, so compact Harold spaces, where the closed open sets separate points. And this duality is induced. This duality is induced by mapping a stone space X to the clopens of X. And under this duality, the Vietoris endofunctor on stone spaces corresponds to an endofunctor on Boolean algebras, which is of interest to logicians because its algebras are precisely model algebras. And the coalgebras for V are the descriptive frames, which essentially gives semantics for model logic. Okay, so this already. Okay, let's see how it works on objects, this duality. So if we map a stone space X to its Vietoris hyperspace, dually, what does this correspond to? Well, we have a dual algebra A, which are the clopens of X, and this should be functorially mapped to K of A. So the clopens of U of X. What are the clopens of U of X? These are precisely the Boolean combinations of boxes and diamonds of clopens of A. And so this dual endofunctor on Boolean algebras maps Boolean algebra A to the free Boolean algebra over formal symbols, box in A and diamond A, modulo some model algebras axiom that are satisfied in this diamond U in box U, where diamond U, let me recall, is the collection of all closed sets that intersect U, and box of U, the collection of all closed sets that are contained in U. And so maybe here you see the connection with model logic. On morphisms, if you have a continuous function f between stone spaces, this is mapped to a continuous function between the Vietoris hyperspaces. Just take the direct image. And dually, this has a nice description. You take a Boolean homomorphism G, and you map it to a certain Boolean homomorphism. It's enough to say what it does in generators, and it's very easy. Diamond A is mapped to diamond of G of A, box A is mapped to diamond of G of A. And the fact that this is very easy comes from the fact that we can use the universal property of Boolean algebra, of free Boolean algebras, to get a Boolean homomorphism, and this works well with the morphisms that we have. So Boolean algebras, the homomorphism of Boolean algebras. However, so if by any chance we got interested in morphisms which are more general than Boolean homomorphisms, so, or between student spaces, morphisms that are more general than continuous functions, then it might be tricky to define such a morphism here. And this chance happened to us. We got interested into something more general than continuous functions. We got interested into closed relations between student spaces, and I will briefly tell you why. So essentially, we were trying to solve a certain problem, a certain open question. It's not so important to understand it, but there's a duality for compact Hausdorff spaces, and the open question was, okay, can you describe the dual of the Vectorius and the functor on this dual, which is De Vries algebra? And essentially, the authors were stuck because there was not this this nice match between the universal property of the free Boolean algebra and the morphisms on the algebraic side. And closed relations came up important, essentially because a compact Hausdorff space can be represented as a Stone space together with an equivalence relation that tells you how to quotient the Stone space to get a compact Hausdorff space, and this is closed. Moreover, a function between compact Hausdorff spaces lifts to the covering Stone spaces not as a function but as a relation which satisfies certain properties, among which being closed. Enclosed here is just a closed subset of the product, or equivalently a subset such that the preimage of a closed set is closed, so just like for continuous function. And the forward image of closed set is closed. Actually, my way of understanding this is the forward image of compact set is compact. But in Stone spaces, this is the same thing. And also, this holds for continuous functions. The forward image of compact set is compact. So this is quite a natural generalization of continuous functions, which also has a nice feature that is self-dual. So if I have a closed relation between x and y, just flipping it formally, I get a closed relation from y to x. And yeah, I'm not the only one talking about closed relations in this conference. So you can see also there are a pair of titles which contain CR, which stands for closed relations, also in a couple of abstract. And let's see what is the base duality for closed relations on which we're building. Closed relations on Stone spaces correspond to subordinations on Boolean algebras. I couldn't refrain from saying that also in the quant-free setting this made a lot of sense because these are precisely the preframe homomorphisms, also known as Scott continuous functions. And maybe this explains why these subordinations, also called approximate mappings, are also important in domain theory, so start with the work of Scott. Anyway, what's important for us is just that we have this duality between closed relations and these things called subordinations. And to explain them, let me start with a picture. If I have a closed relation between x and y, then what is the dual? Well, it's a relation from clopens of y to clopens of x, and it essentially tells you, okay, give me a clopen v and a clopen u, and I will tell you whether the preimage of v is contained in u. This information is enough to recover the closed relation R. So for example, the equality between two Stone spaces corresponds to the inclusion of clopens. So the way to think of this subordination is as a lesser equal, but possibly between two different algebras. And in fact, the axiom of subordination are very similar to the lesser equal. So a join is S related to a matrix if and only if each disjunct is related to each conjunct. And we have this duality, so Stone duality extends to equality between close relations and subordinations. Good. And what's interesting is that the Vietoris construction has a nice extension to closed relations, which essentially is like a nonlinear construction, but between two different sets. If you have a closed relation from X to Y, okay, I should give you a relation between the Vietoris hyperspace of X and the Vietoris hyperspace of Y. So give me an element of the Vietoris hyperspace. So a closed set here and a closed set here. And these are in relation if and only if every element here is related to some element here, and vice versa. And this restricts to the usual Vietoris functoron continuous function, so the forward image. Okay, so main question, what is the dual of this? Right, we cannot use anymore the trick for functions, but still we get something nice. Okay, so we should give, given a subordination from A to B with an algebra, we should give a subordination from Ka to Kb. So a relation. Now just think of K. Ka is the clopens of some Vietoris hyperspace. Kb is the clopen of some Vietoris hyperspace. And remember that the subordination are like less or equal. So let's do something a bit simpler, and let's see how we can compute inclusions of clopen subsets of a Vietoris space. So if I have a stone space X, and let's say I want to understand when these conditions happen, and I want to understand it in terms of things that happen in X rather than Vietoris of X. And well, the fact is that any such equation can be solved algorithmically, and the key idea is that we can go to a system of inequalities of this shape. So if we get an inequality between a finite conjunction of boxes and diamonds and finite disjunctions of boxes and diamonds, which furthermore has exactly one box here and one diamond there. And moreover, we have a certain side condition which tells you that every AI is containing B and C is containing each BI. Then something magical happens, which is that a certain clearly sufficient condition, which is that AI is included in C or B is included in DJ. This is clearly sufficient just by monotonicity of diamond and boxes. This happens to be also necessary. And so if we arrive at a system of equations of this type, then we can solve it. And we can do it always. So for example, here we can apply this rule. Then we get a union containing something. So we can split it into two equations. I've written on two sides. And now we're almost in this setting, so we have an intersection of diamonds and boxes, including a union of diamonds and boxes. It still doesn't satisfy the side condition, but there's an easy way to make it possible. So in the diamond A, I add intersection B, and in the box D, I add C union. And then we can apply the key idea. And on the other side, I get something that always holds. So the solution of that inequality is just I intersection B included in C, or B included in C union D. Okay, and And that's what works for describing the dual of the Vietoris and the functor on closed relations. So it's an functor on the category of Boolean algebras and subordinations. On objects, it's the same as we've seen before for continuous functions and for Boolean homomorphisms. You take the free Boolean algebra over these formal symbols, quotient by model algebra axioms. And on subordinations, it maps the subordination S to the unique one that satisfies this diamond or box with box idea. So here we have to replace the inclusion of S down here and the S of S down there, but the idea is the same. Either one of the diamond element is in relation with the diamond element on the right, or the diamond element on the left is in relation with one of the boxes. Okay. And yeah, as an application, we could solve this problem. I have some bonus slide if you're interested in it. But let me give you what I want to convey with this talk. So first of all, in certain aspects, it might be good to go beyond functions and consider closed relations or dually subordinations between Boolean algebras. This was useful for us in De Vries duality. And also, the Vietoris dual has a nice dual also in this setting, given by this formula diamond with diamond or box with box. And yeah, if you want to see how we package this idea, you can look at this paper joined with Bezanichvili and Karai, where we provide the Stonewall description that I presented in the previous slide, and as well as a De Vries dual description of the Vietoris of the functor. Okay, and if you want to squeeze all this information in just one sentence that you can bring back home, just remember that Vietoris is a nice book. Thank you.